Hi, Anna. First of all, can we record your presentation so that we can have it later on? We have a YouTube channel, and we would like to share it with all, and then we will post it on our YouTube channel. So welcome all. Yeah, we are here. Hi, and we are thankful to Dr. Garcia Armada for accepting our invitation to be here with us today. She is the IEEE ComSoc VP for Member and Global Activities, and also a professor at Universidad Carlos III, Spain, Madrid. The seminar title, abstract, and bio have been sent, but let me now make a small review of the bio. She is leading the communication research group. She is widely known in ComSoc. For the ones who you don't know, recently in Globecom last week, she was awarded the outstanding award for her amazing work within ComSoc. She has been secretary and chair for the ComSoc Women in Communication Engineering Standing Committee. Many positions in her university, management, deputy director, I see here, vice chancellor for international relations and director for the department. Okay, many visits to international locations, hundreds of publications. So we are, I think you all know Anna from the community. She is an outstanding member in our community, and we are thankful to her for accepting our invitation and give us the talk today. So Anna, thanks again for accepting the invitation. It's our honor to have you here, and please, the floor is yours.
Thank you. Thank you very much for the invitation and for your kind introduction, and for this opportunity to know a little bit more your thesis, because I think we have a lot of common topics, and I would probably like to get more involved in the future. So this talk is my particular view about how we went from mobile multimedia broadcasting or to the present, and how we will go in the future to the tactile internet. And first of all, well, you, Nizar, already introduced me, but let me say that I work in Madrid. My university is called Universidad Carlos III de Madrid. That's the name of a king. And we are based not exactly in Madrid city, but a little bit outside Madrid, which is the capital of Spain. And my research group is called the Communications Research Group. Actually, it's quite a small group, and we focus mainly on physical layer. You will see physical layer, MAC, but my talk is going to be a little bit more general, focusing on many collaborations with many people and industry with whom I've learned to grow above physical layers. So hopefully this can be of interest for many of you, not only those that are working in the physical layer. Before we start, and just as a teaser, so to hopefully convince you to stay a while in the talk, I want to introduce to some nice ladies that, as you see, this one and the next one are really having a great time. And they are smiling, right? And if you want to know why, you need to stay a little bit longer, and they will come a little bit after. But before that, let me go a little bit back in time to a time when we had two completely disjoint mobile communications. So we had a communication system for broadcasting, and a communication system for voice, and afterwards exchange of data through mobile communications. And actually, the mobile and the multimedia broadcasting was the first one to acquire or embed a new waveform that is going to happen to appear a lot in my talk. It is OFDM, very well known for all of us, but at that time it was not that well known. So Based on the experience gained through these multimedia broadcasting services using OFDM, we managed to understand the channel effects, to understand the synchronization needs of this waveform, understand the effect of phase noise and how that could be corrected. And actually, this is still an important topic today. The peak to average power ratio, so the high peak of this waveform, and many others. And based on all this knowledge that we accumulated, it was possible, since the first use of this OFDM in DVB-T, to move towards mobile communications in LTE. This is probably the first time that these two services started to converge in terms of physical layer. But before that, they had already started to converge in services. Why? Well, at the beginning, when we were trying to send information to several users, even if it was the same information, we had to use a system where we had one link to each of the users, one link in the core network, one link in the transport, and one link in the radio, which was completely inefficient if we wanted to multicast or broadcast the same service, the same information. But as early as in the latest steps of standardization of UMTS 3G, the 3GPP adopted a system that was called MBMS, Multimedia Broadcast Multicast Service, where this was not needed anymore. And it was possible to have a single link in the core and transport, and even in each of the cells, to communicate the same information to the same users. So this was the first convergence, I would say, convergence in the way communication is conveyed. And this was greatly improved when we came to 4G, to long-term evolution, LTE. This MBMS evolved to the eMBMS in the 3GPP releases 9 to 14. And there were several changes. There were changes in the architecture. So in the packet core, which was called Evolve Packet Core, there were new nodes taking care of this broadcasting of information. There essentially some gateways and some servers. But there was also new changes in the mobility management. And I think what probably was more interesting were new changes in the radio interface. Because the adoption of this OFDM, it was possible now to do single frequency networks, which were called MBMS, single frequency networks. And because of that, it was possible to not only address with one single signal all the users in one cell, but to address with one single signal all the users in a big area composed of several cells. This, of course, needed some tailoring of the OFDM signal, and concretely, there was the possibility to have an extended cyclic prefix that was needed for these big operation areas. But this was a disruptive change in the mobile radio access. Now, at that moment, it came the important question of how to improve resource allocation of the OFDM if you want to do multimedia broadcast multicast. Why? Because OFDM allows a very efficient distribution of the physical resource blocks, that's the groups of subcarriers, in general to single users, right? But how to accommodate different users that are receiving the same signal? Usually, we could have a very conservative approach and just make sure that all of them are able to receive the signal, but this, of course, will penalize those users that could have better quality and could achieve a higher bit rate. And at that moment, the solution was to include several different broadcast multicast groups. That means when you have the scheduling, there was the possibility to establish different groups that will all receive the same multicast broadcast signal, but in each group it could have a different rate depending on the quality of the users that were grouped in this in this group. So this, of course, is a combination or a trade-off between two possibilities. One possibility is complete broadcast multicast, so you have one group, everything goes to everybody at the same time with the same quality. In the other extreme, you could have several unicasts that was happening at the beginning, each of them possibly with a different quality, but using a lot of resources. And in release 13, there was this multicast operation on demand that introduced a trade-off. So it was possible to decide between unicast and multicast for every particular situation, making the best possible use of all of these words. So this brings us to release 14, which is the latest LTE or LTE Advanced. And at this moment, we have pros and cons, right? So we are with this OFDM and this multicast broadcast system, we are now able to completely efficiently use the resource allocation. We can have a flexible unicast, multicast, depending on the needs. And this thanks to the signal that was used in LTE and that was tailored to these possibilities. Now, still in this stage, release 14, there are difficulties for high mobility, and it's possible, very feasible, that we want to communicate in vehicles, even fast trains. This is not clear how to do this at this step. And also there was not any or not much emphasis in reducing latency in this at this moment, right? And the question, of course, is can we still do this with OFDM, or do we need changes? Maybe perhaps even a completely different waveform. So, well, we have many new solutions that appear with 5G. In 5G New Radio, for the first time, we have 3 cornerstones of different services, and we have the possibility to adapt our signal so that all these 3 different services can be accomplished. One is the usual mobile broadband that in 5G is called enhanced mobile broadband, like the classical services in mobile communications. But at the same time, we have massive machine type communications, opening the door to the IoT and the industrial IoT and the communication of millions of machines. And last but not least, the ultra-reliable low latency communications that will open the door to all this possibility of connected vehicles where we can relax and avoid any concentration on driving. All these new solutions allow us to even imagine new possibilities that will probably be in the intersection of all these 3 cornerstones, and almost essentially everything we can think of today should be possible to be accommodated either in the first releases of 5G or in the subsequent ones. So this was an interesting and important change. And how is it possible, right? With the same signal, how is it possible to accommodate all these different scenarios? So for example, how is it possible now to really have high mobility? And can we really have high mobility? Because if we still have OFDM, and it is the case, right? 5G still, new radio has the same OFDM signal that I started with in my talk. But we know well that if we have high mobility, in OFDM, we would aim to have short symbols, because then the channel will not change in between the symbol, right? And what about latency? Well, it's essentially the same idea, right? If we want to have low latency, we want to spend little time in transmitting each packet. So again, we would like short symbols. But OFDM, at least in LTE, is completely adapted to the multipath, and the symbol duration is adapted to what is the maximum expected multipath that we are envisaging to find. And actually, the cyclic prefix is also tailored to that. So what is the fundamental change in 5G? The fundamental change is called the numerology. And it is an interesting way to be able to really adapt our signal to this scenario. So if we start with a long OFDM symbol duration, which is what we have in LTE, a long symbol duration means small subcarrier spacing, so subcarriers are quite tight. But of course, we could maybe have a symbol duration that is half of it, and then that means the subcarriers are spaced twice this spacing. If we go even one step more and we have half of that length, subcarriers will again be more separated, and well, we could be like this, you know, forever until, well, until eventually the symbol is too short and the subcarrier spacing is too large to even be feasible. And this is actually what we call the numerology in 5G. So in theory, we are able to select what is the best subcarrier spacing and symbol length. So maybe we have an outdoor macro cell where the multipath is big because the space, the scenario itself is big, and we want to have long symbols. But as we go down to smaller scenarios, maybe, or most probably, it makes sense to have smaller symbols that will have will be enough for the multipath, but will have other advantages. And with this, we can have this tool to adapt our signal to whatever the mobility and the multipath are. But we may wonder, what about latency? Is this also helping us with latency? How is latency related to the duration of the OFDM symbol? Because actually, not necessarily it is, right? I mean, if it is, of course, related, but the problem is that most of the protocols and the algorithms that, and procedures that happen in the mobile network, even at the physical layer, relying a two-way communication. So we need uplink and downlink, and we need to fulfill both to really have completely closed the loop. So then what really matters in the latency is the distance between the uplink and the downlink. And what happened in LTE? In LTE, there was a definition of a slot that was 14 OFDM symbols that was fully fixed. So you could have an uplink slot, which all the symbols devoted to uplink, or a downlink slot with all the symbols devoted to uplink. But then, between one uplink and one downlink, you needed to wait for the whole frame to happen, right? So the limit of the latency is not the symbol, is the frame. What about 5G NR? Well, now this is another big change, because now it is completely flexible how you want to configure your slot. And actually, there are more than 50 format configurations. So you can have as close as you want the uplink and the downlink. Not even only that, you can also have mini slots that can be as small as only 2 FDM symbols. And this allows a very fast scheduling. So indeed, now we can really have a small latency that is completely related to the length of the symbol. So if you have longer OFDM symbols, you have longer latency, but it can be reduced thanks to this numerology. So then we may wonder, well, okay, so where or what situations can we really have these shorter OFDM symbols? And I would say, especially when frequency is high. And why is that? Well, in one sense, when the frequency is high, we are going to have shorter range communication, right? Shorter distances because of the high path loss. On the other hand, when we have high frequency, we absolutely need beamforming, because otherwise we cannot counteract this high path loss. And when you have a very narrow beamforming, you have much less multipath. So in both cases, because of the reduced distance and because of the beamforming, the multipath is going to be reduced in these higher frequencies. This allows us clearly to have shorter OFDM symbols, making use of these larger numerologies. So millimeter waves in 5G NR, which are still not very well deployed, at least in Europe. We are still, particularly in Spain, we are still waiting for the auctions of the frequencies, but they are expected to happen right now. Is probably something that we really need to be able to really accomplish this low latency and high data rate communications. That would be the evolution of what we had at the beginning. With this millimeter wave and with this 5G new radio, we have now all the key enabling technologies that will allow us to completely personalize this unicast delivery, because we may be able to have all the resources needed to have the same a particular information to each of the users. And what are these key enablers? Well, one, of course, is the bandwidth, right? So if we go up in frequency, we have much higher spectrum availability, and we are able to offer higher bandwidth to everybody. Another one important enabler is the beamforming. As I mentioned, these high frequencies really need that we are able to use an antenna that focuses the transmission to the particular users, and that needs advanced beamforming, which of course we have already developed quite a knowledge about that, but I would say to have this in high mobility is still challenging. We have also in 5G the network slicing. This is very important because we have different services, and we may have these services that I'm mentioning that have very strict requirements, and the possibility to have independent resources for these particular services, independent from others, which is what network slicing does, is an important enabler. And also for the low latency, it is not enough that the transmission happens fast. It's not enough that the symbols are short or the processing takes place fast. We have the propagation, right? And even the speed of light is fast, but it's not fast enough to go very far away in milliseconds, right? So we have also this important enabling technology of the multi-access edge computing. With all these important enablers, we have tried a project with some colleagues, and in particular with Nokia here in Spain, that we call AMATISTA, and I would like to tell you a little bit of what we found in this project. So in this project, we have been using an immersive music therapy based on virtual reality in a nursing home to help elderly people that are starting to lose a little bit their ability to react to sensitive inputs. And we used, in particular, a pilot of millimeter waves, even though they are not deployed here, but we were lucky enough to have this possibility to do several things. One important one is to understand the what is the modulation and coding scheme, what is the numerology, how to do the beamforming in these millimeter waves, and try to validate some simulations that we can use afterwards, even if we don't have the possibility to have the prototype or the real world measurements. We were able to do this validation with measurements, and more importantly, we were also able to understand how this important technology can be helpful for the people, which is, I think, at the very end, what we work all for, right? So let me show you a video, but I'm not sure. Let me check, because maybe I didn't take care to share my sound, and it is important to share the sound. So let me just maybe I should stop sharing and share again, so I can make sure that I share.
Yes, please. Or maybe if you share directly your desktop.
Yeah, I think now it should work. Let's see if it works, because now you see again my screen, right?
We see it.
Segovia, viva mi tierra. Segovia, viva Segovia. Segovia, viva mi tierra. Por esto de Champú nos gusta vivir en ella. Nos gusta vivir en ella, Segovia, viva.
It's a bit longer, but since we don't have that much time, I just wanted to, I think you saw, right, that we had a millimeter wave base station that was transmitting towards the residents. And not only we were able, to experience with these elderly people to see how much they improved, because they actually improved the way they react to stimuli, because, well, when being exposed to the music that they had when they were young, also we were able to analyze new possibilities, right? Because when you have a validated simulator, you can check things that you don't have the opportunity to check in the real deployment, because the deployment was in a particular scenario, right? For example, we were very interested to understand how much you are losing with the concrete configuration of the beamforming, that the equipment that is now available in the market can perform, right? And it turned out, in the particular scenario that I'm showing here, you were losing quite maybe up to 5 dB. But also we were very interested in understanding in what situations it could make sense to have two radio frequency chains in the receiver, in the mobile device, to be able to do a 2x2 MIMO. And actually, in the particular scenario of the resident, which was very line of sight, it didn't make sense. It was not possible to multiplex two simultaneous different beams. And we had to go to a much more dispersive scenario, which is the one I'm showing here, where actually we see here that we have higher throughput if we have two RF chains than if we have only one. But this is at the cost of having a lot of losses. So at the end, we needed a very high signal to reach up to 1 gigabit per second in this particular. So, well, we developed some understanding, because, as I say, this has not been deployed yet here, and it is important. So in this moment, with these experiments, what we had was just virtual reality. But what about augmented reality? So being able to really interact with your there are some processing that can even be done in the cloud, in the far cloud, because they are not so latency constrained. And here we studied what is the processing that each of these different algorithms require, and we try to figure out what is the requirement for the radio. Meaning, is this possible with today's 5G new radio, or do we need to wait? So what you see here is we analyzed for several different cases, depending on what we offload to the MEC, what is the peak throughput that we are going to need in the radio, and what is the round trip time latency that we are going to need in the radio. And this depends, of course, on what is the processing time that we are able to do state-of-the-art devices that are doing all this processing. And if this processing is relatively large, so in the area about 10, 14 milliseconds, what we found is that this is very demanding to the radio. So actually, it may be even difficult to do in 5G because it is more than 1 gigabit per second. The latency goes down to 2 milliseconds. But with what we consider to be state-of-the-art devices, we find it is possible with 1 gigabit per second, which is something that we can get in 5G with the millimeter waves, and the latency of 4 milliseconds. That is also possible. So our proposal to do this is an architecture where, again, the 3D reconstruction can be done in the cloud, but most of the processing is done in the MEC, the hand tracking, the semantic segmentation, the simultaneous location and mapping, occlusion, and all this. And in the radio, if we have a particular configuration of a 5G new radio where there are some TDD configurations, 34 to 42 or 50 to 55, that prioritize uplink because the uplink here is very demanding, with a subcarrier spacing of 120, that is numerology 3, and the bandwidth of 400 megahertz that should be soon available. We can do this in millimeter wave. That is where this high numerology is allowed in the standards, and of course with a network slicing that properly reserves our resources. So at this time, we are able to do this. We have a small prototype, but we found that really there was a need for an emulator, because not always you can try this, right? Not always there is, especially at this time, millimeter waves are not yet deployed. And it is very important to be able to try some specific use cases, those that most likely could accelerate the development of these technologies before actually the infrastructure is deployed. So based on all this experience, on the measurements, on the simulations, we were trying to find some tool where we can handle in real time actual IP traffic above 1 gigabit per second, when also we have many simultaneous users that can be at least hundreds, that can be at the same time sharing the same resources, which is something that we should find in reality, right? We didn't find any. So that's why we developed an emulator where it's specifically tailored to test application level experiments that are going to use these technologies. And you can have, this is an open access emulator that you can download from the GTAG of Nokia. And actually there is also a lot of explanation of how to use it, but also we have a paper that is just being finished and will be a magazine paper that will explain also how to use this emulator and some of the details I'm going to present. It is an emulator that completely mimics from the physical layer to the PCDP, and also allows to inject either generate synthetic IP traffic or inject traffic that has been captured. And it has some simplifications, right? Because in order to be able to run so many concurrent users and at high speed, and especially the simplifications are more in the physical layer, where we have several assumptions. One of them is that we have a time step of 1 millisecond. We don't do anything below 1 millisecond. And of course, we have the possibility to emulate many different scenarios, line of sight, non-line of sight. And we estimate analytically experimentally the SINR, but then analytically the modulation and coding scheme. And based on the rank, we are able to determine what is the throughput that is going to be feasible in each of the links. So you are free to use this simulator anytime, and of course contact us if you have any doubt. We have validated this simulator with measurements, with the real millimeter wave measurements that we were lucky to be able to do with the Nokia team. And actually, as you can see here, measurements and model are very, very close. And actually, the mean error is about 5%. And also, in order to be able to analyze more different situations. We compared with some of the state-of-the-art simulators that allow very precise simulation, but don't allow to have hundreds of concurrent users, 1 gigabit per second, and low latency. And actually, we simulated 2 scenarios, one more in the C-band, 3.45 gigahertz, one in the millimeter wave, and we found very, very similar results. And then once this is validated, what happens? Well, this can be used effectively as we wanted, right? To have an emulation of many concurrent users. Actually, we can have hundreds, but many hundreds, up to thousands of users. Depending, of course, on the configuration, but we have a deadline of 20 seconds in which we need to emulate the whole thing. And we are able to do this for any kind of frequency, very big broadband, and a lot of users. Okay, so I'm close to concluding, but until now, what I presented is more or less how we went to where we are and what is the current status, right? And I would like to have also a view, a look into the future. Because until now, we have developed a huge expertise in conveying acoustic information, auditive information, as well as visual information. But those are, of course, not the only senses we have, right? Humans, we have smell, we have touch, we have taste. Actually, these paintings are paintings in El Prado Museum in Madrid, where there was a very interesting exhibition last summer. It was called The Essence of a Painting, an olfactory exhibition. And you were able, with this kind of device, you were able to smell the different fragrances, up to 10, of one of these paintings. And then I thought, well, if it is possible to reproduce all these smells, we are quite close to being able to transmit them, right? Because, well, we just need an orthogonal basis, as we all know, right, of smells that can, as a combination, a linear combination of some essential ones, be able to reproduce any of them, and there are devices that can reproduce them. And this is where actually I would like to work in the future, towards an internet of senses. But of course, what do we need for that? We need, of course, bandwidth, even more than we have in millimeter waves. So probably we need to go to terahertz. Terahertz is a difficult technology, a very short range, but it's time to start developing for sure. It may not be ready for 6G, maybe perhaps for 7G, we will see, but it's time to start. But I think we have another technology that is much more mature, which has also high bandwidth, which is the light, right? And in particular, visible light communication. And I think probably in our way towards the Internet of Senses and in our way to 6G, this visible light is going to be more tightly integrated with the radio frequency. What else we need? Well, we need big antennas, large antennas, with respect to the waveform, right? We need an evolution of massive MIMO towards probably ultra massive MIMO, and this is needed if we want to go to such high frequencies. This, of course, has many problems. We start being in the near field rather than in the far field, and we need a new understanding of how waves perform in these circumstances and how to do the beamforming. And probably also we need a little bit more flexibility. We need to be able to reconfigure even the channel. This is what is now very popular with the reconfigurable intelligence surfaces, but maybe not only reconfigurable intelligence surfaces are the way to reconfigure, right? Maybe they have given us a clue of how we can go. But more importantly, we need to determine what is the waveform. And the good question is, we came from my first slide up to now with our companion OFDM, but will it be a good waveform for 6G and for this Internet of Senses? This is debatable, right? And in my particular view, but of course, there are many views, I think if we really want to have very fast communication, high speed, and in 6G, I've seen the requirement of 1,000 kilometers per second. Maybe we need to revisit not coherent communications and have a combination. Not only non-coherent, of course, when you can do coherent, you do coherent, but have a combination and not always be based on sending pilots, because for very high speed, the amount of pilots, the overhead can be completely hampering your communication. And also, if we want to go to very high frequencies, we have the problem of the amplifiers that are expensive, are non-linear, and I think there are many interesting new waveforms that are OFDM based, but have constant envelope, but truly constant. I'm not talking about a small PAPR, I'm talking about fully constant envelope, and actually there are several of them. We have a couple of recent papers that are already available in early access. You can have a look. And in particular, this one that is called frequency modulated OFDM has the advantage that it works also in high mobility. So it has almost everything. But of course, these are possibilities, and most likely there will not be just one unique waveform for 6G, but a combination. But let me go back to the reconfigurability. I mentioned that perhaps RIS is not the only way. And actually, we are working and we are quite excited with the possibility of having the antenna to be completely and fully reconfigurable, which is a part of the transceiver that still now we didn't reconfigure, right? And we're working in liquid antennas. Liquid antennas are made of liquids that are metals that are liquid at room temperature. And let me show you a very quick video in our lab where we have a column of E-gain, which is an alloy that is liquid at room temperature. And as we enlarge the column, the frequency where the antenna resonates is changing. And here I'm showing you a way to move this liquid that doesn't need any pump, because of course you don't want a lot of mechanical devices in your mobile phone. But is it possible to move this and to change the shape of this liquid antenna using just electromagnetic field, our signals, maybe a DC bias? And actually it is. I'm showing in this video, this movement was done purely with an electromagnetic input and not without any kind of device. All these are enabling technologies to finally achieve what we call integrated communication and sensing. Because if we really want to be able to sense completely our environment, and we need to convey all this information, but we probably don't have enough resources to do separately the communication and the sensing, and it is very important that they converge. And actually, there is a lot of interest these days in these topics. Well, the good news is that work is underway. Actually, I mentioned this need, to have an orthogonal basis of olfactive information. Well, maybe not for olfactive, but for haptic communication. There are already groups that are analyzing how to actually do the source coding, right? Because it is fundamental that we don't just transmit the raw data, but we compress it as much as possible. Otherwise, it will be completely impossible. And there is also a very active tactile internet group in IEEE. And well, there is a lot of work to do. And actually, this is good news, right? Because this is why we are needed, the telecommunications engineers. We are needed to advance these communications to frontiers that maybe we cannot even envisage today. And also, I believe we are needed to facilitate the life of people, which I think should be our main target. And with this, I conclude. Here, just some references that summarize part of the work that I explained. that has been done with the help of a lot of colleagues and projects and industry colleagues, in particular Nokia, and also many students. So thank you for your attention, and I will be very happy to answer any questions.
Thank you very much. Really an enlightening talk. Okay, so many interesting topics. We really like it. So if you have any question, you can directly unmute your mic, but I see here that we have already some question in the chat. So the first one, and I will read them. Okay, they're good. So the first one question says, for this AMATISTA project, wouldn't it be better if we use wire? What is the purpose of using a millimeter wave or wireless?
Well, yes. Well, this I say always to my students, right? If there is a cable, use the cable. But the problem is where there is not a cable, right? And there are, these locations are usually these elderly residents, or they are not always in a place where you can arrive with a fiber, right? And in many places. And so that's why, of course, yes, if you can, for sure. But the key here is that you don't need it, right? So if you don't have a cable, you can as well have a quality that is almost as good as what you could achieve with a fiber.
Yes, very good. Yeah, for sure. There is, I see, another question related to millimeter wave. Abdul Hamid is asking that in the video it's shown that the millimeter. So is it line of sight?
Yes, exactly. It is line of sight, and actually we are not using a mobile phone because, well, we didn't have any, right? Now they are coming. So it is a CPA, a much bigger device that is outside the building. And then inside we have to use Wi-Fi or whatever. So actually, in the simulator, we wanted also to check, right? Is it possible to achieve this communication indoors through the windows, which happens to be quite difficult, actually, right? Because even the windows, it depends what kind of windows, but these windows that are weatherproof, they have a lot of metallic things, and it's really difficult. So yeah, this project is it's actually fixed wireless access, which is actually the first use case in which millimeter wave have been deployed, in particular in the US. In Europe, probably we don't have this need, not that much. At least in Spain, we have broadband by fiber in many places, and our operators don't see that clearly, that they need this fixed mobile access as a key enabler of 5G. So then that's the question, right? Where are we going to use these millimeter waves in Europe? Probably in hotspots, but in this particular project, yes, it is line of sight.
Okay, thank you. I see here another question, but okay, so there's a question that says 5G is NOMA or OFDM? NOMA or OFDM? I don't want to answer, so you can answer. Please.
Yeah, it is OFDM. There's been a lot of research.
I agree with that concern, yeah.
It is because NOMA looked very promising, right? And there were, as far as I know, because I'm not very much into NOMA, I have to say, but what I perceived is that there were so many different NOMA possibilities submitted to the 3GPP that none of them was selected. And maybe it was too early for NOMA, because there are many works in NOMA that prove that you can achieve. They focus on the achievable rate. But yes, you can achieve that. With what modulation? With what receiver? I think there is a need to go more to the practical details. And probably in 3GPP they already went, but maybe they didn't find a good solution yet. So by now it is OFDM. Let's see what having different users in different frequencies. It is true that non-orthogonal access theoretically has a higher multi-user capacity. This is true, but it is true that the OFDMA is not that far. And if you have all the practical implications, well, what we see is that this is what we have at the moment, right? So those that work in NOMA, I encourage you to try to think a little bit more on the practical side, because the theory is encouraging, but until we find how to practically do this in a scenario with a lot of users, it's still way to go.
Yeah, I just add one comment to Sharif, who asked this question, that Professor Garcia here, she was talking about 5G NR. So in NR, the standard clearly says OFDM, okay? Maybe in the future, as she said, okay, I was interested in the Internet of Senses. Always I have thought that video and is the one that really consumes data rate in Internet of Senses. So for the other senses of smell and so on, I always had in mind that it will be, you know, smell. So it will be something discretized, and the need for large data rate will be low. So I wanted to ask for your opinion about that. Because you said that they will need terahertz. So do you think that this would be the case?
Yes, but I think I agree with you. I think it is more video, but the video, not of ourselves, but the immersive video, right? Being able to locate the whole surrounding around us and interact with it. This is what I think at the moment is going to take terahertz. And also, if we can be represented by holograms, and well, there are some initial experiments, right? And it depends, of course, on the size of the holograms, but the amount of data rate they are using is huge. So what I see here is that there is a lot of need to understand better and compress. Because, well, this happened also at the beginning of voice and at the beginning of video, right? We were using far more bandwidth that was strictly needed because we were just digitizing in a naive way. So there is a need to understand much better. And this happens also with the other senses. Because if you don't understand and you cannot have a reduced amount of basic information, and you really need to convey all possible smells, for example, well, all possibles are a lot. so I think we are like in the beginning of this new era, where we have to go all the way that we already did for the video and for the audio, and that took us ages. I mean, it took us 1 century. So now we need to accelerate a little bit more based on all that we know now to be able to do this.
I fully agree. Okay, thank you. So I'm checking if there are more questions on the chat. I don't see. I have a small comment for so for all the people attending so the FICO array, the name of the simulator. I saw that there is some kind of draft on archive, so you can search for it, and maybe you can get more information. But also, yeah, you can contact Professor Garcia Armada for more information.
Yes, please feel free to use it. I mean, the emulator is for you to use. So
very interesting.
absolutely.
Yeah, anything that is open access usually attracts people initially to make a double check if they would like to make any upgrade. And it is open if anyone makes some development so that it can be added up.
That I'm not sure, because you know it is Nokia. So I think it is open to use, but I'm not sure it's open to even contribute and modify. That I'm not fully sure. But at least it's open to use, you know, for whatever you need. Yeah.
Sounds very good.
I'm not sure. So in the GitHub, it's probably all the information. Perhaps it's even possible to modify the update, but that I'm not sure. Yeah.
Okay. So I check again. So yeah, so that we have no more questions. So we come again to thank you for your time, for accepting our invitation. It's our honor to be here and to listen to your interesting talk. And yeah, please be aware that we will be posting the video on CSIM website and YouTube channel. And look forward seeing you in the next seminars. So thank you all. Thank you, Anna. We appreciate everything. It has been really nice. Thank you very much.
Bye.
Thank you. Bye-bye.